Okay, so I think we can start. Whoever will join, they will like catch up, and we'll have a recording on the BirdSex website, as I mentioned before, as well as a presentation on PDF. Well, my name is Jorge Casir. I'm the project manager for this new project BirdSex, and I would like to introduce my colleague Guillaume Berson, who is going to present the first webinar about the APRS mission competition that we're going to have inside of the satellite. So Guillaume, you can start. You are muted.
Damn it. Okay. Good morning, good afternoon, and good evening, everyone. My name is Guillaume, as Jorge introduced me, and today I will present you the BirdSex project, and more specifically the APRS mission that we will be holding for the next years. So let's start. First, table of content of the presentation. We start with the presentation of the team, then an overview of the satellite and its configuration. Then we will talk more about the APRS competition, more specifically the payload competition. That is why you are here, I believe. Then also a bit about the ground terminal competition, and we'll finish with all the questions if you need to ask some. So first, the BirdSex team. We have, of course, Jorge Casir, the project manager from Mexico, Marisa Koziakou from Thailand, and myself, Guillaume Berson from France. APPU from Myanmar, Sarah Aziz Garab from Egypt, Miyaji Masuta from Japan, Matsui Tasku from Japan, Marco Panetti from Italia, Javier Ferrer from Paraguay, Tarindu Dayaratna from Sri Lanka, Etsunakar Yudai from Japan, and lastly, Inoue Miyu from Japan too. As for the satellite overview, BirdSex mission is in the lineage of the BIRDS project held by the Lassen satellite in QTech. The goal of BIRDS in general is to bring diversity to space sector and democratize the use of space. And this mission emphasis specifically is the promotion of satellite usage and amateur radio community, since our stakeholders are QTech as well as the ARDC that I will explain a little later on. We have 4 different missions, the 2 competition, APRS payload and ground terminal competition, as well as 2 other missions, the APRS student mission and the UHF new transceiver that will not be explained tonight. As for the satellite, we have 1 satellite of 2 units based on the BIRDS bus. The approach from the Lassen laboratory is the LIN satellite, and the team is composed of students, as presented before. As for the operation, we would use the BIRDS ground station network built with the last missions. The more technical specification of the satellite, as a 2U satellite, the dimension, external dimension of the satellite is 100 by 100 by 237 millimeters. For a total weight of 1.8 kilogram, this is after simulation, 3D simulation, so it's a minimum we have now, and it will increase as we develop the satellite. We have also some specification about the solar cell type from Azuspace, as well as its efficiency, around 30%, electrical performance with maximum voltage, maximum intensity and power, and the cell connectivity. We'll have 16 cells connected 2 by 2 in series, and for a total of 8 series of in parallels, which is a total of 16 cells. As for the battery type, it will be a nickel metal hydride batteries with a capacity of 200 milliampere hours and 1.2 volts. Lastly, the communication specification is for the communication with ground segment. We have where we use UHF, ultra high frequency, which is above 300 megahertz. For our mission, we'll use the frequency of 435 megahertz for uplink, and downlink will be held with 437.375 megahertz, with a downlink and uplink rate of 4,800 bit per second. We'll use 4 different antenna, two very high frequency, between 30 to 300 megahertz, and 2 UHF frequency above 300 megahertz. All of them will be dipole antennas. As I explained before, one of our stakeholders is the ARDC. ARDC is the Amateur Radio Digital Communication. This is a private foundation that aim at enhancing and improving the amateur radio and the digital communication. Since there are funding our projects, we will have a focus on telecommunications. That's why our four missions are radio communication and concentrate on radio amateur frequency. Then I will explain what APRS is, because it's what the competition is about. APRS is stands for Automatic Packet Reporting System. This is a specific type of radio communication that use a universal standard format and one frequency per country. This allows all the APRS stations to work as a network that can repeat. We call it digipeating all the packets they receive to improve the initial range of all the packets that are sent. Every APRS packet can have different information. You have here some example: position information. This is the historical use of APRS. Text messages, emails, weather information, bulletins, emergency alert, and scientific data. The difference is APRS cannot be used for voice messages. For the type of radio wave and modulation, there is a little specification. So APRS use the X25 protocol, which is audio frequency shift gain modulation. You have a little diagram on the bottom that explains it. And we'll use a TNC, a terminal node controller, to do this modulation. This is important because this is a part that will be in the future APRS transceiver that will be designed for the competition. And usually the performance for APRS is around 1,200 bytes per second on very high frequency, so between 30 to 300 megahertz. For the packet format, as I said, it's a unique packet format for every APRS packet. It starts with a call sign, which is the call sign of the source. Every station that use amateur radio frequency have a call sign to identify themselves. It's followed by the path that the message followed before arriving at its destination. As I said, every packet can be repeated by station, and every station that digipit the packets are listed in the path. Here you can see that 4 different stations digipit the message before it arrived at the call sign destination, which is the third information in the packet. And the last information is basically the content of the packet. Here it's a simple little message, 73 standing for hello in the amateur radio community, with the name of the person sending the message. This packet was received from ISS, which is one of the most reliable and known station in space for APRS packets. So to continue with the overview of the satellites, and we deep a little more in the design of the satellite. Here we have still the dimension of the external dimension, as well as the orbits. We'll use the ISS orbit since the satellite will be launched from ISS, which is around 400 kilometers from the ground, with 51.6 degree of inclination and a roughly circular orbit. We will launch through the program, the JAXA's program G-Cube, that launch CubeSat from the ISS, and we will use exclusively amateur radio frequencies. As for the design, you have here some screenshot of the 3D models of the satellite. The external view, you can see there is the 4 antennas, dipole antennas. They are grouped by pair of 2 on panels that are opposed to each other. And you can see in black, the black tetragon is the solar cells. They are by pair of 2, and each pairs are in series, and there is 8 in total, so 2 times 8 is 16 cells all over the satellite. On the right, you can see the frame, which is an aluminum frame. On each corner, there is the rails, which are aluminum, of course. And between each rail, we have the mounts that ensure the structure of the structural integrity of the satellite. Inside this structure, we'll have the payload of the satellite. As you can see on the bottom, there is, maybe let me show you with a pointer. So at the bottom here, you can see there is what we call the backplane board. This is the spine of the satellite. And on this backplane board, there is connector where we can connect each board one by one. This use of backplane board reduces the needs of cable and harness that reduce the problem that a satellite can face. Here on the right, you have what we call the bird bus. It's composed of the battery, the OBC, and the UHF transceiver, as well as the two front and rear access board. This is the vital organ of the satellite, because the OBC, the onboard computer, is the brain that will synchronize every component of the satellite and treat every incoming uplink command that will be received by the UHF transceiver that you have here. In the middle, we have the 7 APRS board. 2 of them will be developed by the BirdX team for other mission, yes. And 5 of them will be reserved for the APRS competition and will be designed by the 5 winning team of the competition. The last UHF transceiver is the new one developed by Tarindu-san. It's a low-cost UHF, and that may hopefully in the future replace the old UHF one. Even more properties with a repetition of the weight and the dimension, since it's a very important aspect, as well as the center of mass of the satellite, which need to be in the middle of the satellite, at least in the cylinders of 20 millimeters of radius. This is one of the JAXA constraints. There is a lot of them to be able to send the satellite in the ISS. As for the materials, as I said, the structure is in aluminum, and the PCB is the FF4 materials. You have here an overall project timeline. We will refine it a little more in the next slide. But as you can see here in green, there is the competition. And in yellow, this is the design of the satellites that BIRDS teams will do for the next years. So 2023 will be the year of the competition. After December, there is still 2 months of testing before we hand over the satellite to JAXA. But the competition will finish around the end of December. As I said, BirdX have 4 missions: the payload competition, the ground terminal competition, and as well as the demonstration of the low-cost UHF transceiver and the APRS student. We'll only present the 2 first ones. I will only present the 2 first ones. But if you have questions and you want more information about the 2 other ones, we can answer, of course. First, the APRS payload competition. This is, I think, what you are for here today. So the APRS competition has one objective. Is to increase the size of the community, of the amateur radio community, and also helping people to get involved in the creation and operation of such a space payload to improve the technical skill in the technical skill around space and system engineering. So what the competition is about is to develop what we call the board, which is basically a PCB board printed with all the components needed to create APRS transceiver. This is a schematic, a basic schematic of an example. Of course, it doesn't have to follow this one, but the goal, yes, is to develop this kind of board. As you can see on the board, there is different components. The board itself, on the board there is a MCU, main control unit, which is the microprocessor that will process all the information coming out and in of the board. the TNC, as I explained, the terminal node controller, as well as a transceiver. The terminal controller will modulate the signal, output audio signal, and the transceiver will transform it in a radio signal that can be transmitted through the antennas. There is different switches, as you can see, to turn on and off the board. And some of them will be requirements, so we can control through the satellite the power output and the power input of the board. There is also a FM, what we call the flash memory, to store all the incoming data so that the satellite can later on access this flash memory to send back the data. This is, of course, a draft of the design, and every team has to come up with their own, and this is an example of birds. Here you have the dimension of the board. This is the requirement in terms of size. You have to abide 85 by 85 with different hole and cut in the board to fit in the satellite, as well as the position of the connectors that will be used to connect to the backplane board, as I explained before. You have here preliminary design, 3D design with here you can see the transceiver and the MCU. It's not specified here, but there is also a specification about the thickness of the board. A BCB is basically 1.6 millimeters, and the transceiver is here. The transceiver in this example is 12 millimeter thick. There will be limitation in the size of the components because we have a limited space for each board. All this information will be in the ICD, the interface document that will be published just after this webinar for you to start the development. As for the competition by itself, we have here the timeline of the competition. We are actually in the call of participation until for the next month. And this call of participation is only to retrieve all the application form. Then the phase one, we start where we select the team based on their application form. And I will explain later on the different criteria. In phase two, there is, after the phase one, of course, come the phase two. This phase two aimed at selecting only 10 teams that will compete for phase three. And it will require what we call a proof of concept. After phase two and the selection of these 10 teams, there will be a final selection, a final selection of 5 teams. These 5 teams will be the ones sending the payload in space. And we will require what we call an engineer model for the end of phase 3. And once the 5 team has been selected at the end of phase 3, we will require the construction of the flight model that will be used for integration and testing. And then we'll have the launch and the on-orbit competition. That is the last part of the competition. So the phase one of the competition. So phase one is this phase actually where we are receiving all the application form. As you may have see before, we don't have any limitation in terms of numbers of teams selected in this phase. This phase is more about the application and to to keep only the more serious team. We'll ask in the application form the composition of the team, an affiliation for latest MOU, a basic mission definition, a payload block diagram, as I shown before, but your own, of course, a preliminary budget plan to show that you can sustain the mission, a schedule for development that will fit the schedule we already have, a plan for outreach, since the overall goal of the BirdX mission is to create advertisement and grow the community of radio amateur. We ask each team to contribute with outreach and through social media, for example. We will take into consideration the quality of application and we'll ask for a consent of opacity. This preliminary selection process has started at the end of December when we published the first document, and will finish at the middle of March 2023. We will provide for the first phase several webinars. This is the first one. there will be at least two other one until the end of the phase, and we will publish several documents, for example, the ICD, which have more specification, more technical specification on what is required. Here you have a more detailed schedule. We are on the 14th of January here, and until the end of January, and until the end of February, you can send your application. The deadline is the last week of February, and for the two first week of March, we will review the application and announce all the selected team in the middle of March 2023. Here you can see the point allocation for phase 1. Since the BIRDS is about developing the space technology and knowledge, we give a little advantage to developing country as well as student teams. That's why we have 5 points for developing country and 5 points for team composed of only students up to master student. A mix of professional student will be 3 points, and professional only or PhD student will be 2 points. The motivation, objectives, expected outcome, and mission definition are valued 30 points. And there is 10 points allocated for block diagram, concept of operation, primary budget plan, schedule, plan for outreach, and the quality of application. In quality of application, we added video explanation if one of the team think that having a video to explain the mission and what they want to do to be more exhaustive and more clear, they can add it, and it will be accompanied the 10 point of quality. I see there is a question in the chat. We will answer it at the end of the presentation, of course. For APRS payload competition, so to continue with the competition, phase 2 we'll continue on phase 2 with the following required documents. We'll ask for another system block diagram. This one more detailed because for phase 2, each team have to develop what proof of concept, which is basically developing a breadboard model with the basic components selected and showing that they can reproduce a transceiver without developing any PCB. That's why we ask for a more refined system block diagram, a base of materials with the list and reference of all the components they want to use, a feasibility study and a function test showing some result about transmission and reception, a safety compliance about the requirement that will be in the ICD, another schedule more refined based on the precedent result, a more refined, of course, plan for outreach, and also showing proof of outreach, and at least a definitive budget to show that they can definitely sustain the whole competition and missions. During this phase 2, we'll continue to hold webinar and publish new ICD with more detailed as the competition is continuing. We'll have a pre-selection for among all the teams that will be on the phase 2, since there is no limits on the number of teams that will be here at this phase, but we will have a pre-selection, and this pre-selected team will have a presentation, and this presentation will determine, and after this presentation, we select 10 teams that will continue for phase 3. This phase will start after the announcement of phase 1, so in the middle of March, and will be finished in the end of May. There is 2 months of development for the proof of concept, and on the first week on May, this is the deadline for the documents. Then we have 4 weeks of evaluation period, and then we publish the result for the 10 selected teams at the end of May. Between brackets, you can see that there is 11th team possible. It depends on the quality of the application, of course, and we can ask more team to have more flexibility for the next phase, of course. This is the point allocation for phase 2. We allocate 20 points for the system block diagram, we ask for something more detailed than the previous one, that the example, for example, more detailed than the example I showed before as point of comparison. A bill of materials with all the component and their characteristic, it's 5 points. And then we have 10 points for feasibility study, 10 points for the power budget, for the mass and volume, the concept of operation, and preliminary link budget, which is basically the difference of, which is the, sorry, I have to explain, which is the sensitivity and the power of the transceiver. For the safety compliance, we allow also 10 points. We ask also the teams to show that their system are not too much of an interference for other payload, and we'll continue to take into account the quality of submission, the schedule, and the outreach, 10 points each, and 5 points for the quality. So the last phase is the phase 3. This phase we see 10 teams compete for the 5 last slots for the launch of the payload. During this phase, we will require an engineering model, which is basically a printed PCB with all the components on it and a working transceiver. This is only engineering model, since the flight model will be a different one, even if the two designs are very close to each other. We also ask for another functional test report with the engineer model, a software operation manual for the MCU, since you have to program your own you have to program the transceiver. Another link budget, schematic and PCB design for the 3D integration. A power budget to explain the power consumption of the payload according to our own power budget, and the compliance to all the requirements previously settled. At the end of this phase, all the team need to send their engineering model in QTech so we can test it and try to integrate it into the satellite to evaluate them. This phase will finish in December 2023, because in phase 3 we also account for the flight model development. But we have here a more detailed schedule. As you can see, from the end of May to the end of August, the 10 teams will have to develop their EM board. And at the end of August, they will have to send the documentation as well as the EM board to QTech so we can test it. And during the 2 next months, September and October, we'll evaluate the board with testing the board in the satellite. And at the end of October, the 5 selected team will be announced, and then they have 2 other months to develop the flight model. And at the end of December, the flight model should be shipped to QTech so we can do the final integration for the handover to JAXA in 2024. As you can see, there is a 6th team in between brackets. We can also ask a 6th team if they want to develop the flight model, even if they are not sure to send it to space. This is a fail-safe for us, so that if one of the 5 selected team have problems and fail to deliver a flight model at the end of December, we have a 6th one that can also develop and ship a flight model at the end of December, even if this team is not sure to be sent to space. This is, of course, based on the willingness of the team, and will not impose anything. Here you have the more overall schedule of the competition from the beginning of January to the end of December. After this competition, we'll have the on-orbit competition, which will aim at select the best payload based on its performance in space. So once the satellite is deployed and all the different scenario has been are already finished, we'll start the on-orbit scenario. The on-orbit scenario is composed of 8 phases. The first one being testing the satellite and the ground terminal and APRS reference with the VHF antenna 1. The APRS reference is our own payload. It's to test the functionality of the satellite before we try anything else. Then we have the same test, but with another reference with the VHF antenna 2. This VHF antenna 2 will be the one used by the APRS payload of the competition. That's why we need to test it as well. Then after this test is successful, we'll send what we call the control data through the UHF so that we can store it in the satellite and use it for the rest of the competition. This control data will ensure that all the packets are the same for all the APRS payload so that we have a fair point of comparison for everyone. Then we will switch on the first APRS mission payload out of the 5. And this, the first one will send the control data received previously to the reference ground terminal, RGT. That will be the ground station, the ground terminal in QTech. We will, so the transceiver will have to downlink this control data to the ground with its own transceiver. And then the reference ground terminal will send back another data to the APRS payload. This part is to test the uplink capacities of the APRS. So we have the downlink capacity test first, and then we have the uplink capacities test in second. Once everything has been received, we send all the data as well as the state of the satellite through the UHF to have all the data needed to evaluate the payload. And we switch to the second payload that will do the same things in a loop. And once all the APRS payload that has been tested, we can redo this scenario as much as we can for a minimum of 4. So we have 4 try to communicate with the payload, with each payload. So we have enough data to evaluate the satellite. For this mission, we have BirdX have its own success criteria. The minimum success would be that at least 4 boards are selected and sent into space. The full success will be that at least 1 mission payload succeeds in communication, both transmitting and receiving, with the reference ground terminal. And the extra success will be 4 mission payloads succeed in all the 4 mission payloads succeed in communication with the ground terminal. That's all for the APRS payload competition. I will go quickly on the ground terminal competition, which is the other competition that BirdX will be holding. The ground terminal competition have more or less the same objective, which is about radio amateur community and the democratization of space. Since nowadays only the ISS is the only reliable and accessible source of APRS in space. So for the detail, we ask at the beginning of the ground competition that will be held later in the lifetime of the satellite. We will ask through a Google form all the information of the applicant, which is the call sign, the name, the address, the nationality, contact info, and as well as the station information, which is the hardware reference of the station, the radio information, the station type, if it's fixed, mobile, handheld, if the TNC is hardware or software, and other information such as the antenna information, position, and picture of the hardware. All this information will be used to evaluate based on the entry category. Each entry category are divided based on the power output of the station. The first category will be up to 25 watts. The second will be up to 50 watts, and the last one will be up to 100 watts. I think these numbers change because, for example, in Japan, 50 watts is the maximum for any radio amateur. So I think there is, yeah, there is an error anyway. APRS band is in space is 145.825 megahertz. This is the same bands for everyone that tried to send APRS packet in space, whatever is the country you are in. So it's true in Japan, as well as in Europe or America. And that's also what band we will be using for the APRS competition, payload competition. The terms of participation, as for the terms, we ask each participant, they will have 1 week to contact the satellite based on the schedule we made according to the different entry we have previously. The participant should provide proof of communication to receive any kind of evaluation. So they need to send through the website their log file, the elevation data, since it's one of the criteria for evaluation, and the power output during transmission to be sure that they are being set in the right categories. All the communication should be performed following the good radio amateur practice and the competition rules, of course. Since one of the rules is all ground station operator must have a valid license in their country. Of course, the participant must provide correct information, and also in order to be evaluated, the complete packet must be exchanged and verified. So what we call the QSL confirmation. For the scoring, so for the scoring, we have different rules. First, we ask any participant to not use terrestrial gateway, what we call terrestrial gateway or internet gateway, which is sending message through internet to connect to APRS network, or to use other gateway station to forward the message. Also, the satellite, each message that the satellite can digibit will be worth 1 point for each participant and must be completed and verified with a two-way exchange, of course. And the format of the message should be APRS packet format, of course. Here you have the scoring. So every contact are worth 1 point, but there is a multiplicator. So, for example, the antenna type, if the antenna type used is omnidirectional, is 2 points, is 2 times the width, and if it's only directional with a tracking system, it's 1 point. This system of point has been settled since we value more versatility and accessibility than the complexity of the system. That's why, for example, fixed are worth less point than handheld radio, or that evaluation angle, the lower it is, the better it is, because it shows that the station is more versatile and more accessible. Also, we take into account the cost of the station, since we don't want overpriced station to be too advantageous, have too much advantages during the competition. I think it concludes the presentation now. Thank you for your attention, and now we can answer every question you have. You have here the link for the website where most of the information, all of the information actually, will be published, and a QR code to access to the website. Thank you for your attention and to listen to me. And now we can answer the question.
Okay, so can you please raise your hand so we can give the word to whoever has the next questions?
check out the
Namira, could you ask your question, please?
Hello, this is Namira from Bangladesh. I'm quite confused about the term handheld. Can you please explain?
So handheld radio is basically the radio that is on battery that you can have, as the terms say, in your hand. It is, do I have an example? I don't know, but it is the radio basically that, for example, policemen have on them to transmit with others. So it's not a fixed one in the desktop. It's a small one with battery. Is it clear?
The portable one.
A portable one, yes. But the difference between handheld and mobile is that mobile can be a bigger station fixed on the put into a car or a truck. So it's more powerful than a handheld, but it's still as mobile as a handheld radio. That's the difference.
Thank you, I got it.
Okay, there is another question from Karma. Could you please say it? And then we go to Blas.
Thank you, everyone. Thank you for the wonderful presentation. I'm Karma from Bhutan. Just wanted to get some sense of what kind of support is available from the competition in the various phases, both in terms of technical support as well as if there are financial support. And then in phase 2, if you look at the scoring criteria, there is also points for available budget. So wanted to get a sense of what kind of amount are you looking for? Thank you.
So when we say we evaluate the budget, it's not about the quantity, but more about is it realistic, and is it fitting the purpose of the mission? Because to build and design the payload, you need to, of course, buy different parts and send commission to companies to design the PCB for you, which means that you need a certain amount of money to be able to compete in the competition and to develop the payload. So we are not evaluating the amount of money you are putting in the project, but more if it is realistic and if you can sustain it. Because if you don't have enough money, or you don't have a budget well planned enough, then it can be later on an issue if you don't have enough money to finish, for example, your board when we need it. So yes, we don't expect any kind of budget for anyone. It is as much as you think is needed and as much as you need, of course, and based on the different choice you made during the design. For example, you can choose more expensive parts than other competitors, so you will need more money, or you choose more a cheaper company to print your PCB, so you'll need less money than others. So yes, we are not evaluating the amount of money. As for the other part of the question, which was about the support, so as said, for technical support, we'll hold webinar and we'll publish documentation regularly. The first document will be published quickly during the beginning of next week, I believe. In this document, you will have all the information specifically about the requirements in terms of power consumption, in terms of the size of the payload, of the size of each component, the maximum size of the components, for example, as well as other specifications such as the required switch, the numbers of pin you need to use, things like that. We will regularly update the documentation and publish regularly new updates, of course. We also have on the website frequently asked question, and if there is any question between webinar, we are also open on social media, and we have email address if you have any question to ask. We don't plan to have any economic financial support to the team. They have to finance themselves. That's also why budget is part of the criteria on phase 1 and 2. I hope it answers your question.
Thank you. Yes, answered. But just have a follow-up question. So in phase 3, what kind of support is provided? If selected, yes.
Right. So phase 3, there will be continuous webinar, of course, because we'll have to update our safety requirement. It came to moment that, for example, the JAXA requirement change regularly. So if there is new requirement from JAXA, we'll have to update our own. So that's an example of the update that we'll have. But in phase 3, we'll continue with webinar. And normally at the end of phase 2, since the phase 2 is about the engineer model, everything should be settled in terms of documentation, which means that during phase 3, we normally don't have any updates about the technical detail of the board, because engineer model and flight model, even if there are two different models, are usually very close to each other in terms of design, because these are the critical time of the development. So in terms of technical support, we'll continue to answer questions if there is any, but since the development will be very very far in the development, normally there is no major update in the design. I hope it's
also to complement this economically, if really necessary and if proven that you need some help, we could maybe we're in talks about like helping with the procurement of some parts for the board. But that is in case it can be really proven that it's necessary, and in the third stage of the competition, the third phase, not at the beginning, but already at the end.
Awesome.
Okay, so if the question was answered, now we can go with Blas.
Yes, hello. I have a question about the hardware of the APRS PCB. In a previous slide, you showed that there will be a MCU, a TNC, and a transceiver. Yes, this slide. This TNC should be a hardware TNC or maybe a software TNC?
Good question. Yes, so as for the choice of the design, as I said, is open to everyone. So yes, there is option to have software TNC, and of course, we are open to every design. Here we put a hardware one because it's the same design as previous mission, but you can use a software TNC as well. Yes, I hope it answers your question. This is, of course, not a definitive design. Every team can come up with their own design, with their own ID, and the reference of the MCU, the reference of the TNC, the reference of the transceiver can be chosen. Whatever is the team, as long as it's fit into the requirements that we will provide.
Okay, thank you.
No problem.
Is there any other question? Okay, there is a question from Rafael and from Luis. We'll go with Rafael first.
Okay, thank you. I have one question. My question is, the data that we will send will be given by you, or we can add some sensors in the board in order to send that information additional.
Yeah, thank you for your question. So as for the information, as I said, during the competition, we'll use control data so that everyone sends the same data during the competition for evaluation. But once the competition is finished, we plan on letting the team use their APRS payload as they wish, of course. I think we will have schedule, and they will ask for permission to operate their payload, so we can let them operate the payload when they need, and when we can allow this time, and for the satellite, of course. But yeah, after the competition, we can let the teams operate their own payload. As for the use of sensors in the board, that's not something we thought about before, but I believe as long as everything else is working fine and all the requirement and development is fine, why not? But I think it will be difficult to I think it's not even possible because the information line that will be assigned into the board will be limited to a certain extent. So using sensors, I don't know yet. Maybe someone else of the team have answered, but I think it will be difficult, if not impossible.
I mean, as Guillaume says, like we have like a standard communication protocol, right? And as long as there is within the power budget and also the space that you have in the board, I think it's possible. But like, I mean, we will have like more details in the ICD that will be provided for like this stage. So, I mean, you can have the proof. We will ask at some point for the proof of concept. So if it really works with the power budget that we are allocating to the teams, then I think it could be a go ahead from our part.
Okay, thank you.
Okay, so we can go with Luis now.
Okay, hello. Thank you very much for the nice presentation, and all was clarified. Just have a few questions, specifically related with this diagram. As it showed there, I see flash memory, right?
Mm.
So as I hear, as you present, we must design an APRS payload for make digipeater, right? Digipitting. But so what is the necessary to use the flash memory? Is also compulsory to make a store and forward mission or something like that?
Yes. So yes, we need a flash memory because there will be a dimension of storing and store and forward. Because during the competition, at least, when a data is received by the APRS board, we need to re-download it by UHF transceiver to see the quality of the transmission. If there is, for example, loss of packets, and to see the speed of transmission, parameters like that. So we need the APRS board to be able to store its own received data into a flash memory that can be later on downlink through our own system. So it needs a flash memory that can be accessed by the MCU, and we can request the MCU to send back the data to the bus system. So yes, there is a store and forward dimension to the system.
Okay, I see. So just for, maybe it could be a future question, but can we just filter just some ground station could make or can access to the flash memory? Because if every radio amateur could transmit to the satellite, maybe, I don't know, one time the flash memory could be full, and the packet, for example, for the GST ground terminal competition could be delayed, right? You understand my question or my point?
I understand.
So we can make a filter, or each packet of each APRS packet may be transferred to the flash memory.
Mm-hmm. So to answer your question, usually the APRS board will be on only for 1 on bit. So every time the satellite pass over Japan, we have a window of 10 minutes to operate it. And we will, through a uplink command, switch from APRS to a board to another. So yes, in 1 orbit, usually the flash memory is enough to not fill up during 1 orbit. And another thing is the satellites, to say it, we will not, we can choose to, we can have a system to save the flash memory system, the flash memory. We can save its data to the flash memory of the satellite. And this flash memory in the satellites cannot be rewrite without the consent of the MCU. So you can implement a failsafe in your own MCU to prevent that also. So the flash memory to be full is less likely since we are only allowing communication for only one orbit.
Okay, thank you very much.
No problem.
Also, in addition, for the ground terminal competition, we will use the reference payload that we will develop like in QTech. So these APRS boards are for a different competition. From the ground terminal, we will use the one that we will design.
Also.
Okay, thank you. Thank you.
Okay, so we can go with Kafi.
Hello, Jorge and Berson.
Hello.
How are you?
Good, thank you.
Thank you.
Thank you.
And nice. So I just need to clear some confusion. So for each APRS boards, that will be used only for receiving, right?
Receiving and transceiving. There is downlink and uplink.
Yeah, downlink will be through UHF, right?
No, as you can see here, let me show you with the pointer. Here, there is these 2 points. So the UHF part will only downlink the data received by the APRS transceiver that you design. So first we send the APRS mission, what is called here APRS #1, will send the control data to the ground terminal, so downlink capacities, and then it will receive another data by the reference ground terminal for the uplink capacities. So it has to downlink and uplink.
Okay. And in total, there is 7 APRS board.
Yes.
5 for the competition and 2 will be developed by the QTech.
Yes.
And how you are going to change the antenna?
Good question. I didn't show it the diagram in here, the overall diagram, but so for there is the 2 reference APRS that we will design. One of them will be connected to his own antenna. So there is only one antenna for this payload. So it's a direct connection. And the 6 other payload will be switched by a RF switch, so a radio frequency switch. This switch has a particular design that allow 6 entry and 1 out and switch between different line based on the input the analog input we put in. So, and this input will be managed by our own site.
MCU boss.
By the mission boss we have. So yes. Yes.
Oh, thank you. Thank you very much.
No problem.
Thank you, Kafi. If somebody else has another question.
I think there is also a question in the chat that has not been answered.
I think we already answered to it. The handheld and Karma, like I answered to most of them. So
okay, my bad. Yes.
Oh, okay. There is
the record of the chat. I would just want to. The record of the chat will be available also with the record of the webinar on the website. So
Blas
if you want to see
another
the question.
So Blas, go ahead, please.
Yeah, I'm sorry. This question has already been answered, but if we talk to the IARU to manage our own call sign, is there a possibility to transmit with our own call sign from the CubeSat, from the BirdX CubeSat?
As for the detail of the license, I think I cannot answer. I know that the license of the satellite will be provided for the whole satellite and each of its payload, but I don't know about the call sign specifically. Maybe someone else have the answer for that.
I mean, as mentioned before, as far as I understood, all of these licenses will be given by Japan, so the call sign will be a Japanese call sign that you can then after access, like of the payload. From your ground station, you need to use your own call sign given by your country. So right now, there is the information that we have, but we will inquire more on it, and then we can give more information probably on the ICD.
Okay, thank you very much.
Yes, Kiran?
There were a question on the chat first.
Does the satellite has any kind of ADCS?
That's a good question. Yes. So as for the ADCS, there is none, because as you can see here, there is the four antenna, they are by pair of two, and these pairs are facing away each other. So if we implement any kind of ADCS, at some point the satellite will be facing only one way, and it will decrease the sensitivity of the antennas because it will be facing away from Earth, one of them. So at first we considered putting ADCS, and then we abort the idea of having ADCS because of the antenna layout. We need the satellite to be tumbling so that every antenna are periodically facing Earth so we can communicate with it. But there will be some kind of gyro sensors maybe on the satellite so we can provide information about the tumbling of the satellite. But it will not be a consistent and persistent part of the mission.
Okay, we can go with Kiran, I think.
Okay, thank you. So I just wanted to clarify all the APRS payloads through the competition. Each of these boards will be provided with the regulated voltage.
Yes.
So have you decided on whether each port will be provided with 5 volt, 3.3, or there is options available?
So as for the option, it's most likely that the board will be will have only 3.3 volt because it's one of the it's either 3.3 or 5 volt or both of them. It depends on the I don't remember what we decided. I think it's both of them. So we will have one 3.3 volt line and one 5 volt line available. And the problem is, can I show you? Yes. So the thing is, we need to be able to shut this line down through switch. So we have a control over the power transmission, right? And if we allocate two lines, so the 3.3 here and the 5 volt, this is the two same line. But the 3.3 and the 5 volt, if we allow two line, we need two switch. And switches are, we need some place to put the switches. For now, one of the switches will be on the outside of the board, so we can control it directly through our own satellite. And one of them will be on the board. It will be one of the requirements, so we can control it inside of the board through our own digital line. So for now, most likely it will be 3.3 and 5 volts.
Okay, thank you for that clarification. And also just a general comment, because you mentioned that each of the payload design is required to have a flash memory to store the messages that it receives and transmits. So from what I see, each of the board, you will have a UART connection between the mission boss and the payload.
Yes.
So will it be a shared UART, or like what would be the interface between each mission board, each APRS payload and the mission board? Because from looks of it, just a small concern from my side that the satellite bus seems to be getting pretty much complicated.
Yes. So we didn't want it to go in detail about this part, but we can explain. So the here you have a CPLD, which is basically a more complicated multiplexer that can handle a lot of line. So what we'll do is having one mission bus, which is a centralized MCU for all the mission, that will be going through a CPLD to communicate with all the mission board. So all the data will go through the CPLD, then through a mission bus, and then go to the onboard computer that will receive the last detail of the mission, right? And also another thing to keep in mind is that no board would be on at the same time. Only one board can be on at one time. So it means that there is, even if there is a lot of boards, there is only one board that need to be handled at the same time by the mission boss and the bus. Does it answer your worries?
Yeah. We can go then with a question from Blas. You have another question? Or it was
I'm
answered?
sorry, I forgot to
Ah.
lower my hand.
Okay. So then we can go with Kafi.
Hello. So it's related to ADCS. So you don't have any ADC system. So it will be launched from ISS, right? And it
Yes.
has initially it has some forces. So
Yes.
the tumbling will be very much in the beginning. So how you're gonna handle those tumbling at the beginning if you don't have any passive or active ADCS system? Just curious.
We don't plan on handling this
Okay.
because yes, this is basically why we don't have ADCS. Also, I think it will be slowed down, of course, with time, and it is a good thing for us to have the satellite be tumbling because, as I said, we need the antenna to be periodically pointing to Earth. And even if, and by rotating the loss of sensitivity for the antenna during one passage of over the certain point of Earth is not enough to totally cut the communication, at least for UHF, which means that we'll only have a periodic loss of sensitivity, but not a totally loss of communication, at least for UHF, maybe not for APRS. But APRS mission will be a bit later in the mission scenario. So hopefully at this point, the satellite has been slowed down enough to allow more stable communication.
Okay. But if you use just again for just a passive control, so it will slow down a little bit faster than the regular one, right?
Yes,
so, and passive one doesn't have any power consumption.
Yes, yes. So we have I worked on this part of ADCS. So it was we first thought about putting magnets and hysteresis dampers to reduce the speed, the radial speed of the satellite, and then with magnet aligning the satellite with the Earth magnetic field, right? But the problem is, if we align to something, then there will be problem. Maybe we can accelerate the slowing down of the satellite, if I can say so.
Yes.
By letting at least the hysteresis dampers. That's a good suggestion. We can think about that. Maybe yes. Thank you. That's a good one.
Thank you very much.
Thank you, Kafi. Someone else has a question? Well, I think if there is no questions anymore, we can finish the webinar right now. And well, I want to say from part of the BirdSex team, thank you for joining the first webinar. We're going to have other webinars constantly until the end of the first phase, sorry. And as Guillaume said, if you have any question, if you want to rewatch the video of the webinar or access the questions that were asked during the chat, you can always refer to the website, to the BirdSex website, which will be at the end. Guillaume, can you change to the last slide?
Yes.
So yeah, all the information will be constantly transmitted through this website and through the QR code. You can also access this website. Please join the application. The faster you join, the faster you can start developing your APRS payload. And well, we will be happy to have you in our mission. So thank you and goodbye.
Thank you, everyone.
Thank you. Bye.
Thank you. Task, please stop the recording.
Okay.